This conference will now be recorded.
Hello, everybody. Jordan Girth here with the National Weather Service Office of Observations. Thank you so much for joining us for the Satellite Book Club Seminar Series. This is session number 178. The title of today's presentation is Tracking Low Clouds and Fog in NOAA Satellite Imagery. I'm pleased to have Bill Line, a scientist in imagery and the Imagery Science Team lead from NESDIS Star with us today. We'll have a discussion following Bill's presentation facilitated by Christopher Smith, the GOES satellite liaison to the Ocean Prediction Center and Weather Prediction Center. Just a few reminders before we get started. As you just heard, the session is being recorded. As always, there is Q&A after the presentation. Please post your questions in the chat and we will field them in the order they are asked. If you have not signed in with your full name, perhaps you're using an office account, please note your name when asking a question in the chat. We're always looking for future presenters. Please contact the Tower S team, Kashad Bowman and Emily Maddox, if you have something you'd like to share, and the training team can help create training materials that may be unavailable or point you to materials that you may be unaware of. Ross Van Til from the Office of the Chief Learning Officer can help with that. I'd like to thank our Tower S team, Kashad and Emily, the Office of the Chief Learning Officer, the GOES and JPSS programs, our presenter, facilitator, and all of you for being with us today. Without further ado, let me give a little bit deeper introduction into Bill Line, who is a physical scientist for the NESDIS Center for Satellite Applications and Research in Fort Collins, Colorado. Bill conducts validation research and development of satellite imagery-based products and tools. Previously, Bill was a forecaster with the National Weather Service in Pueblo, Colorado, and this year's selectee for the NOAA David Johnson Award, which will be awarded in just a few weeks. So, Bill, happy to have you at today's Satellite Book Club.
Hey, Jordan, thanks for the great introduction and appreciate the Tower S team having me back. I always enjoy giving these presentations. And thank you everyone for joining today. So tracking low clouds and fog and satellite imagery, it may sound pretty basic, and I think that's really important, especially for this audience, to periodically, go back to these basic topics, and because we're constantly getting new forecasters and we may forget things. So I think it's great to be able to update everyone on, what we should be doing or what's available out there to accomplish these tasks. But also at the same time, if you've seen my presentations here before, I like to give some of my tips and tricks or ideas that I think could be helpful to you, the forecaster. So a lot of this is going to be review, but hopefully there's some new stuff in here for some of you that you could take home and use in your office. All right, so let's get started. So what we're going to be, most of this presentation uses imagery from this case from a few weeks ago in January of widespread low clouds across much of the US, and you could see the watch warning advisory map there. Many dense fog advisories across the central US. And I did write a blog, just a quick blog post on this event, and Lee saw it and asked if I would do a book club. So of course, I added a lot to it regarding, again, how you can use satellite imagery to track these events. So I start with this animation because I think I hear a lot of forecasters ask about this type of transition. This is, I think, a very useful type of display, being able to transition between, I think, two of the most popular and maybe two products that every forecaster should be monitoring daily: the nighttime microphysics RGB at night and day cloud phase distinction during the day. This display is available on the StarGOES image viewer. You could just Google that and it'll come up. It's a really great site for viewing satellite imagery. And you may ask, well, I want to do this in AWIPS, and well, so do I. So I tried, and this is the best I could come up with. So you might be familiar if you do your toggle image combo or whatever that button's called, and then you can do a day-night transition between vis and IR pretty easily, and it works okay. You can't do it easily with RGBs. I had to go in and edit the XML file, and this is the best I could come up with. I cannot for the life of me get that transition to line up with the Terminator. So maybe someone out there in the field could try to get it to work, but I think this is something that maybe AWIPS wasn't meant to do with RGBs. So again, it kind of works, but it's not as straightforward in AWIPS or as successful. So I think if you want this type of display for either situational awareness or you really like it, definitely that Star Image Viewer page is a good one to go to. All right, so focusing on nighttime low cloud detection, I think especially the more seasoned forecasters are familiar with the night fog difference. It's really more of a cloud phase discriminator, I would say. Whereas with this display, you're able to differentiate liquid clouds, which are in this difference, the positive values or the bluish areas, versus ice clouds, which are the grayscale or the negative values. And this is what we used before we had GOES, before we had the extra spectral capabilities. But again, you could only differentiate liquid clouds from ice clouds. So where you probably have low clouds versus your more upper clouds or glaciation. Of course, with GOES, that added spectral capabilities, we combined that fog difference with a split window difference and your IR window to get a little more information. And with this type of display, then we could further differentiate those liquid clouds to maybe your lowest level liquid clouds or your fog versus your maybe mid-level liquid clouds that maybe aren't fog, and then your ice clouds from thicker ice clouds and thinner ice clouds. And I did that here, so if you were just looking at the fog difference with this event, you would say, well, here's the liquid clouds over western Colorado, over the high plains, then you've got some ice clouds further to the south. And then with the RGB, you could, again, further differentiate that to see, oh yeah, and I also wanted to point out this area in southeast Wyoming, it's kind of speckly, and you see that throughout the scene. This is relevant, but from this image, you wouldn't notice that. So if we go to the RGB, you could see more of a color difference because you have that split window difference in there, but also because you bring in temperature information. So how deep is that cloud, or what type of environment is that cloud? And so we see over the high plains then, kind of tuning your mind to the season. We'll talk about the seasonal changes with this RGB, but you know that, and looking at surface obs, this bright green to maybe reddish color at times is your lowest clouds in this environment, while these more maybe orangey clouds to the west are more mid-level clouds. And that jives with the surface obs. You're not seeing fog over here, but you are further to the east. So you're able to better differentiate those types of clouds by using the RGB, but then also connecting them to the surface obs, I think, is helpful. And then also the upper clouds you can further differentiate from the thicker clouds and the thin clouds. And this weird area in southeast Wyoming, you actually see in the RGB that it's a cloud. It's some sort of, I think, mixed phase mid-level cloud that wasn't so apparent in the difference. And as we saw from the obs, this was indeed, you could see fog to the east, and then these clouds in the mountains, more mid-level clouds, but liquid clouds with cloud bases around 5,000 to 10,000 feet. So moving on to this example. Oh yeah, so I wanted to really quickly, I really like scouring Weather Service AFDs and seeing how they're using satellite imagery in operations. And this was a great event to showcase how several offices across the high plains were leveraging nighttime imagery in ops. In this case, the Cheyenne office noting that the HER was actually differing from what the observations were showing in terms of the low clouds were sticking around a little longer, so modifying a TAF based on satellite imagery. Further to the south in Boulder, you can see forecasters discussing the evolution of low clouds up the South Platte River Valley, and also the dissipation of low clouds further south around Lincoln and Washington counties, where they had to make a decision to cancel the dense fog advisory a little early, again, based on, of course, satellite imagery and a combination of satellite imagery and observations. In Pueblo, tracking the low clouds creeping up the Arkansas River Valley, and then in Albuquerque using satellite imagery to really see between or beneath around those high clouds, see where you have low clouds creeping a little further west than maybe originally was forecast. And again, using satellite imagery to make a decision to add additional counties to the dense fog advisory. So when I was looking closer at this case a few days ago, notice the low cloud area. This is across Nebraska and western Iowa. For the most part, the obs were indicating the same things, very low clouds with fog reducing visibility. But you saw this weird differential coloration in the field, and I'm always curious why that is. You could see from sampling, maybe you're more familiar during the winter season with this bright greenish color. I think that's a fairly thick low cloud in a cold environment. Embedded within that, you start to see these more maybe reddish tints within the field. And I was like, well, what is that? And then further east, you see the sharp cutoff where you go from the bright green to this almost grayish color. And I was wondering, well, what is that too? Well, if we look at a quick radio sonde from Omaha, you see, as you would expect with this type of event, a pretty impressive inversion. So that might have something to do with it. So once we get to the day, we could kind of confirm what we were starting to think, in that you could actually see as the sun rises to the east, you see this slightly higher low level cloud deck to the east casting a shadow on the lower level cloud deck to the west. So that's one of the reasons you're getting maybe more blue here and maybe a slightly different microphysics. This is a different cloud deck separate from the one to the west. Slightly higher, maybe it's tapping into warmer brightness temperatures as well, causing some of that discoloration. You also see, well, when you have the daytime imagery, you kind of have these semi-transparent areas where you could see closer to the surface. And I think that's another reason, especially these embedded pinker areas where you have less of that fog difference signal. So that might clue you in when you start to see this color embedded, this pinker color embedded within the greens, that maybe those areas are thinner, more transparent areas of low clouds where you're actually getting some signal from the surface impacting the signal in the bands and eventually in the RGBs. So ultimately, yeah, I think that those color variations are due to variations in cloud top height, which is very slight variations, as well as variations in the cloud transparency. So something to keep in mind, and might be relevant, especially if the thickness or maybe the transparency might play a role in your forecasts. This is more of a broader scale comparison. I think we're all familiar with by now, but this nighttime microphysics RGB does vary considerably in appearance, especially for low clouds across air masses. So from maybe summertime in the north to winter time, you'll see those low clouds appear more as a blue to cyan in the warm season, as you could see on this day to the southeast, becoming more bright green, or even, as we saw, maybe some pinks or oranges in a cold air mass or during the cold season. So similar clouds, but different mainly because of the season, and just, yeah, something to keep in mind and remember. I wanted to touch on the GOES RGBs and level 2 product combinations we have in AWIPS. We gave a book club on this. It was session number 84, discussing this addition to AWIPS. And you can access these, we call them GOES RGBs with derived product readouts, these menus from the satellite menu, local menu items, GOES RGBs with derived product readouts, then your sector, And what we did was marry derived products with RGBs. That made sense, so that you view the RGB like you normally would, but when you sample the RGB, you get quantitative information from the level 2 products without having to view them and load them separately. So in these cases at night, we put with the nighttime microphysics RGB, the fog probabilities, which give you probabilities of MVFR, IFR, and LIFR conditions. So you could see as you would sample the scene, these clouds, I think this is on the East Coast, you have your readout of the RGB variables, and then we also have the cloud thickness, saying roughly 1,000 feet, and then very high probabilities within these clouds for all conditions. Then we go over to the clouds to the west, and we see that maybe LIFR and IFR conditions are much less likely, but you still have high likelihood of MVFR. And then maybe we want to see what's likely going on under these clouds to the north, and you see much less likely to have those conditions, those visibility reducing conditions. Now for nighttime, for at least for cloud monitoring, we always talk about where does VIIRS come in? Can VIIRS be useful to a CONUS forecaster? For cloud monitoring, maybe not so much during the day for like low clouds and things like that, just because during the day you have half-kilometer visible imagery, and from VIIRS you have 375, so you're not getting the best bang for your buck. But at night, your IR imagery is 2 kilometer, and you have 750 meter nighttime RGB imagery, and that's 2 kilometer at the equator. So as we get further away from the satellite subpoint, you're stretching those pixels. So you do see a significant improvement in IR imagery, such as the nighttime microphysics imagery, when you go from ABI here to VIIRS here, especially for really localized fog areas, maybe that are just starting to develop. You can see here west of Pueblo near Canyon City, and then in the mountains, mountain valleys, maybe localized areas that harder to detect, or you might be able to detect a little early in the VIIRS imagery. But also when you have multiple cloud layers, I think the high resolution VIIRS is a good supplement to ABI. Obviously, ABI gives you the great spatial or temporal coverage, but with VIIRS, you can maybe add a few images every night to give you a better idea what exactly those clouds look like, maybe newer clouds that are creeping through river valleys or high mountain valleys. Here's further south, many cloud layers in eastern New Mexico, and you can see comparing ABI with VIIRS. Again, at least to me, in the VIIRS, the different cloud layers stand out a little better in the VIIRS imagery. And of course, this imagery isn't in AWIPS right now, at least, but you can access VIIRS and compare it with ABI on the Cirrus slider in the JPSS satellite section if you select the CONUS sector. And one more comparison. This is a really neat one. Further east, looking at River Valley fog, ABI on the left, VIIRS on the right. You can see, temporally, you have great coverage seeing the fog creeping through the valleys in the ABI, but with VIIRS, you could actually see some areas of fog that aren't as apparent in ABI with that higher resolution, very small scale fog situations. So I'll just let this one play, just flipping back and forth. So I do think there's value in low clouds at night situations and checking on VIIRS around the 1 a.m. time when you'd start to get those passes. So here's an example, one more nighttime example, actually from the same day. This was Anchorage office in Alaska monitoring really localized fog around the Anchorage area. Of course, in Alaska, due to swath overlap, they get a lot more VIIRS coverage. ABI pixel size is stretched quite a bit up there, so they do make heavy use of VIIRS in Alaska. And you could see the animation on the right, the VIIRS nighttime microphysics, those very localized areas of fog developing very clear in the VIIRS, but much more difficult to diagnose in ABI, especially early on. And this one is one more back and forth. Tried to time match it as best I could. You can see once you get so far away from the equator, those signals become pretty washed out, especially for smaller scale features in ABI. All right, now we're finally to daytime. This was the next day, looking in Nebraska. Visible imagery, when you've got snow, you've got multiple cloud layers. I think we all know it's very difficult to differentiate those various cloud layers. I am a loyal user of the day cloud phase distinction. Including for low clouds over snow. And you can see in this example, just compared to viz for now, sorry, let's go back. And then day snow fog on the right. Now, I know a lot of people like to use day snow fog for snow situations, and it's great. And I think in some cases, the fog stands out even maybe a little better than day cloud phase. But I like day cloud phase because I think for colorblind folks, especially where you have these areas where snow cover's patchy and where you have snow next to no snow, and day snow fog, it's pretty difficult for colorblind folks, the reds and the green next to each other. Also, day cloud phase uses the 0.6 micrometer half kilometer viz. Day snow fog has the 1 kilometer 0.87, so you get a little more crispness, not Christmas, detail in the low clouds, but also the semi-transparency field, those semi-transparent clouds, it's easier to see through them, easier to see that they're semi-transparent, easier to see the surface underneath with the higher resolution imagery in day cloud phase. But again, I think this may be preference. Of course, day snow fog does a really great job of capturing low clouds and fog as well. But I think take home point, I think we're all doing this, and we all should definitely be using RGBs for cloud monitoring during the day, especially low clouds and low clouds over snow versus just your single band imagery. And here's just, I'll flip between these a couple times. You could see these semi-transparent clouds over the central part of the scene where you could see rivers and snow cover underneath. Pretty neat. All right, we have a recommended from those GOES RGBs with dry product readouts I mentioned earlier. We've got one for the daytime. I think this is a really cool one that connects the day cloud phase distinction with cloud top phase, cloud top height, and cloud optical depth products. So maybe you see a weird color, or you see something you don't remember what this color means, or you just want more quantitative information about these clouds. You load this up, sample these cyan or blue clouds over Pennsylvania, and see that these are super cold liquid clouds with cloud heights around 5,500 feet and relatively thin. If we go further east, you see that these clouds, these bright red, reddish, pinkish clouds are ice clouds with much higher bases, and they're pretty thick. And then, well, maybe you forget what green means, and that's actually clear sky and it's snow. So I think definitely some value in leveraging these level 2 product readout displays. All right, so I do hear a lot of forecasters talk about how it's difficult. There's that difficult time period where the sun's rising or the sun's setting, and you feel like you don't have good nighttime imagery, but you also don't have good daytime imagery. We've talked about this in the past, using, even if you're using single band imagery, but especially you should be using the RGB imagery. You can go in and make a quick modification while you're on shift to make, maybe it's getting later, you're losing contrast in the image because your reflectance is going down. You could go in very quickly, right click on the product, go to composite options, and reduce the max reflectances for, in this RGB, your green and blue components, which are your reflectance bands. Very simple, it should take 2 seconds. And I recommend reducing them to the same degree. So In this case, I reduced each of those components by about 75%. So the max for green down to 20, the max for blue down to 15, and you really do increase the usefulness of the RGB another hour or so. Actually, in the top image, you can barely see the low clouds. In the bottom image, the low clouds are very apparent over northern Montana, Canadian border, over the snow cover with high clouds overhead. So very simple change, takes a few seconds, and get a little more bang for your buck out of the RGB. Here's a back and forth, looking very, very late in the day. And then one more example, over Southeast Colorado, made a similar change as in the previous example. You can see the low clouds in the morning. Now this is a morning example, sun rising. Maybe you lose your IR imagery, so you want to use your daytime imagery, but it's still too dark. You can make that modification and get use from your RGB a little earlier. There's the back and forth. And so we talked about the handoff, switching between the nighttime imagery and the daytime imagery. And I think this modification helps to ensure that you have a useful image from either the day RGB or the night RGB at all times. You're not missing, there's not a gap in where you don't have useful imagery. And so on the right is that same case, we've reduced the reflectance channels max values by 75%. So this is around sunrise. So you're using your nighttime microphysics imagery on the left. This is 1406 UTC, 1411, you're still using nighttime microphysics. You're starting to lose night micro, but on the right you see day cloud phase coming in. So maybe around this time you switch to your daytime, nighttime, or day cloud phase distinction RGB. So again, there's not a period here where you don't have useful cloud imagery. And again, if you hadn't made that modification, it would be a little more difficult to get use out of the daytime RGB so early. So I think that modification is pretty important to be able to get that daytime imagery working a little early when you start to lose the nighttime imagery. All right, this is the last slide. I've shared this before, but it's kind of my hope that we can, in AWIPS at some point, have automated changing reflectance thresholds for your reflectance channels, your vis and near IR, so that in RGBs, they automatically adjust to changing sunlight conditions. So instead of on the left, you losing contrast in the image, you get an image on the right where you kind of maintain quality further into the low light hours. And I think Tower S is working on this, or OPG or someone, hopefully. All right, that is it. Thanks a lot, everyone, for joining, and I'm happy to take questions now or offline.
Thanks, Bill. That was a great presentation. I do encourage everyone to stay on to ask questions. If you're from one of the field offices or regional headquarters or just an attendee, please put your full name in the chat when asking a question. Next week, we will have Scott Lindstrom, scientist and trainer from SIMS, discussing NewCaps profiles in gridded NewCaps at noon. And you can contact the Tower S team, Kashalda Bowman or Emily Maddox, for questions about the Satellite Book Club or configuration of satellite products. So yes, if you have any questions, put them in the chat. Otherwise, I can start off with a question. Bill, you had a lot of great examples. I am the satellite liaison for the Ocean Prediction Center, so I didn't see any examples for that. I just have a question. If the RGBs should perform the same, looking at fog over the oceans, we can use the same tools.
Yeah, sorry, marine tropical forecasting is not my forte, but obviously they should have similar signal over the oceans. The main thing you'll need to keep in mind, especially at night, is your seasonality changes or where you are in terms of air mass, those differences in nighttime microphysics. But also over the ocean, you have a unique tool that's kind of uniquely useful over the ocean, and the ProxyViz product from Sierra. I think that's available at some national centers now. At Sierra, we've developed a GeoProxy product that kind of puts that ProxyViz information into GeoColor. That's available on Slider, at least for now. And that ProxyViz product really helps to highlight low clouds over the ocean really well.
That's great, thank you. And we do have Jammer asking for a live voice question. Jammer, if you want to ask your question.
Yeah, can you hear me okay?
Sounds good.
Okay, yeah. Hi, Bill. Great presentation as always. Correct me if I'm wrong. I would not expect with ground-based phenomena like fog and snow that there would be much parallax error between the GOES view angle and the VIIRS view angle. So I noticed on some of your comparative imagery between GOES and VIIRS, there was definitely a difference between the fog areas at the same time. Can you explain that?
No, you're right. There should not be much parallax. Yeah, there's not much parallax between the low clouds. So you see the shift in these red clouds, which are upper level clouds. That would be expected. These mid-level clouds are shifting a little bit, but yeah, and even these ones to the west are more mid-level. They're shifting a bit, but the lowest clouds here aren't really moving at all.
Okay, so there's a little shift, but it isn't that much.
There could also be some minor scan time differences between these two images. It's kind of hard to match exactly the time of the pass from VIIRS with that location in ABI. But no, you're right. There shouldn't be much parallax from ABI for low clouds since they're at the surface.
No, I'm satisfied. I'm amazing that you can get these two, the VIIRS and GOES images so close together. Thanks.
Yeah, thanks for the question, Jammer.
We did have another question from Brian Curran. He was asking, at what point do you think machine learning or AI will take over and improve RGBs? He doesn't expect to see this in AWIPS, but could the Sierra slider leverage the use of machine learning or AI?
Yeah, that's a good question, Brian, and I know something I think we're all always thinking of this day and age. AI ML isn't my forte right now, at least. I could see it for RGBs. I haven't really seen it. I think at this stage, it's maybe being leveraged to help support certain RGBs. I know NASA Sports done some work with dust detection and kind of marrying that with the RGB. And then maybe AI can help with things like those low light situations and maybe automated adjustment of reflectances. But I think seems, at least my interaction with forecasters, folks will want to, at least for the time being, have the imagery available, because that's the observation, that's the truth, and maybe have ML AI type products supporting the imagery. Good question, Brian. Thanks.
Thank you. We have another question from Scott Lindstrom asking if GOES or VIIRS data is terrain corrected. If they are not, that might introduce parallax issues. He couldn't tell from the image you were showing.
Yeah, good point, Scott. And yeah, it would depend on where I'm looking with the terrain. But so in so yeah, the VIIRS imagery is terrain corrected, and the ABI imagery is not. So you might see, I guess, over high terrain, low clouds shift a little more in the VIIRS versus ABI, since VIIRS would have the terrain correction and ABI wouldn't. I think that makes sense. And yeah, this example is on Slider.
Thank you. I did have another question. I know that you had some overlays pairing the RGBs with some of the GOES fog and low stratus products. Have you noticed any trends for how those products are performing? Are the probabilities that they're putting out for fog, do they tend to, overestimate or underestimate the probability for fog?
Yeah, good question, Chris. First, on the last point, Curtis from Sierra mentioned that on the JPSS CONUS slider, which is what I was showing, ABI data are also terrain corrected, so you have both terrain corrected views and ABI. So thanks for adding that, Curtis. So you wouldn't see any shift or differences on the Sierra CONUS slider due to parallax or terrain correction. I mean, and then on your question, Chris, I don't know. The fog probability is, you'd have to look up the documentation. I know they have verification for that product that I don't know off the top of my head. So certainly something you can look up, I'm sure, online.
Thanks, Bill. We'll leave a couple moments for any other questions in the chat.
Sorry, that was my daughter.
All right, well, if there aren't any other questions, I'll turn it back to Jordan for final remarks. Thanks, Bill, for a great presentation today.
All right, thanks, Chris. Thanks, everyone.
All right, thank you so much, Bill, and thank you so much, Chris, for moderating that discussion. As always, the Satellite Book Club continues, but it's not always on February 29th. So a special leap day version of the Satellite Book Club with Scott Lindstrom, scientist and trainer from SIMS, is going to be talking about new caps profiles and gridded new caps. In the meantime, if you have any questions for the TowerS team about the Satellite Book Club, about the configuration of products and AWEPs, Kashad and Emily are standing by and can help you with that. Find us, of course, you can always send an email, but you can also find us on the National Weather Service internal Slack workspace with the TowerS channel. With that, once again, I will thank Bill, Chris, and all of you for being with us today. As always, thanks for our TowerS team for orchestrating this, and hope to see you all back next week. Until then, take care, everybody.